Who is your speaker? Me? I did medical sciences. My background in electronics, as it says there, spoiler, is none. So what I want you to take home here is that what I'm telling you is from my experience, and if I'm wrong, I want you to correct me, and I want to learn from you. So that's the reason why I put this up here. This should be simple. It should feel like high school physics, which is really the level that I reached, but it's enough to be able to use as a baseline to get you started in figuring out how things work and where problems are. And finally, most of my experiences is with Williams System 11 and WPC, so there might be a heavy slant towards that, but electronics is electronics. It's the same no matter what. So, who are you? Why are you here? Why do you want to attend this? Well, you just bought your first pinball machine and you looked at it and it's like, I don't know how to fix it, something broke. You've opened up the back box, you looked at it and you said, whoa, all that stuff back there, it kind of confuses me. What the heck's going on? You want to learn some more about your pinball machine? Or finally, you're just here to heckle the speaker. So I can tell you the story about me when I bought my first machine. It was, I want to say 2013. I bought it from Chris. It was a whirlwind. Got a couple of buddies. We drove up there, hauled it back in my house, set it all up, played the snot out of the machine. Love it. Still love it. And then one day the flipper stopped working. And I was just like, uh-oh, what's going on here? How do I fix it? So then I posted out, looking for help, asking for stuff, did a little bit of reading, but was really kind of nervous because I didn't know what I was doing. So I've been there, I've done it, I'm where you've been, or where you are now if you're at that stage. We all go through the learning curve. So my invitation to you is if you have questions, ask. The only crazy, stupid question is a question that's not asked, because the answer is you'll never know what the answer is until you ask the question. So, electricity. I see you, can you see me? Basically, you can't see electricity. It's there, you can feel it. Boy, can you feel it when there's 50 volts or 100 volts running through it. But you can't see it. And historically, things that people didn't understand or they couldn't see, people thought it was magic. And people who knew how it worked were geniuses. Well, if you get a little basic understanding on electricity, you too can be a genius, at least in front of your friends. The thing to think about electricity is, like a lot of things, it's a form of energy. When electricity flows, it's just energy being converted from one form to another, and because it's energy, it almost always ends up as heat. It does a little bit of work. You can convert electrical energy into mechanical energy. You can convert mechanical energy into electrical energy, but when you do that, you always convert some of it to heat. And that's why these machines, after a couple of hours of being on, you open them up, it's like, oh, it's warm in here. That's all the heat. So, yes, there it is, Ohm's law. It's the first thing I learned in physics and electricity way back in high school. And it has served me well in all the stuff that I've needed to understand on how these machines work. Voltage equals current times resistance. Voltage is also often referred to as potential difference, and it's electrical potential difference. When you think of, and I think there'll be in further slides, but I'll stop here and say, if you think of things like how high you are off the ground, that's a gravitational potential difference. The higher you are from ground level, the higher your potential. Same with electricity and voltage. The higher you are from the reference, often referred to as ground, the more potential energy you have. So if you're 20 volts and somebody else is at 40 volts, they have twice as much electrical potential energy. But remember, it's potential energy. So it's a little like, well, I'm 20 foot above the ground and you're 40 foot above the ground. That's potential energy. None of it is actually being converted into motion. It's only when you tip yourself over the edge that you start converting that potential energy into mechanical or movement energy. It's exactly the same thing with voltage. But here's the thing again, you can't see it. It's electrical energy. Current is flow, so once you cross over the edge, you fall down, and that movement, that's current. And resistance is like the air. The air is going to stop you. It's going to make it harder for you to move. And and as you know, things start rubbing up and moving against each other. It generates its friction. It generates heat. That's where the form of heat, that's where the energy, the heat energy comes from when we start using electrical energy. And this bottom one here it's just in there because right at the very end, I'm going to talk about electrical components, and electrical components have power ratings. And if you don't put the correct component with the correct power rating in there, you'll release the magic smoke. So here it is, voltage. It's electrical potential difference. Like I was telling you earlier, with the how high you are above the ground, voltage is how high you are above the ground potential reference in terms of voltage. The biggest point that I want to get home with voltage is it's relative. You measure between 2 points, and one of them is the reference point. It's very common that the reference point is ground, but it doesn't have to be ground. So here's the example. I'm on the ground level, and I'm going to use the height level analogy because you can visualize that. You can't visualize electricity. Here's the height example. I'm at ground level, and I go up to the second floor. Now I'm 2 floors above ground. If I go up to the 4th floor, I am now 4 floors above ground, but I'm 2 floors above the 2nd floor. So it really depends on where your reference point is. If you're going to say that the reference point is the 2nd floor, then the 4th floor is 2 floors above it, and ground floor is 2 floors below it. That's the biggest thing that got to take home with voltage and measuring it. Where's your reference? What are you measuring to? It's always between 2 points. And there is such a thing as negative voltage. That's when the other end of the point that you're measuring is lower than the ground potential. And often when we connect things up, we connect it up so that ground is earth, whatever you want to call it. It's the green and yellow plug that plugs into your wall, the ground pin, whatever you want to call it. That is the reference point that's often used for ground. Or in a DC system with a battery-powered device, the minus, the negative terminal, is often the ground reference point. It's exactly the same thing with 2 1.5 volt cells. If I stack them together in series, the potential difference across them is 3 volts. The potential difference at the midpoint is 1.5, and it depends on where I put my leads as to whether I get 0, 1.5, 3, or minus 1.5 or minus 3. It's all relative. So the water analogy is kind of like pressure. The gravity analogy I've discussed, but the water analogy is like, let's say I have a closed system of water, and there's a certain amount of pressure in it. The pressure is like potential energy. It's the higher the pressure, the more potential there is for the water to flow. Kind of, if you can conceptualize that. I prefer to use the gravity one because it's easier to visualize height above ground, but some people can refer to the water one. They can relate to it more easily. The water one we'll use with current and resistance because it actually makes more sense to me, but again, different people's brains work in different ways. So current, particles and charge. Current is the flow of charge. Electrons. How fast it flows, how much of it flows, is essentially what current is. Conventional current, when you draw on diagrams, is always the current flows from the positive to the negative. But that's not the way that the real world works. The current actually flows with the electrons, and the electrons flow from negative to positive. But for all intents and purposes, I stick to conventional current, and I don't bother about the direction of actual electron flow, and you probably should too. One thing to remember is current always flows from the highest to the lowest potential. It's exactly like gravity. You will always fall from the top to the bottom, unless of course you have some magic anti-grav device. But that's the way current works. It always flows from the highest to the lowest potential, and that includes negative. Again, it's about a reference point. If I'm on the 4th floor, I'm always going to fall down to the second floor. And if I'm on the second floor, I'm always going to fall down to the ground floor. Even if I consider the second floor as my reference ground point, I'm still going to fall from the second down to the ground, or from 0 to -2. That's how it works. It always goes to the lowest potential. So the water flow analogy is like, you can't see the electrons flowing in the wire. Again, even this can't see the electrons. It will show you that they're flowing on its display, but you won't be able to see them. The water analogy is, you think of the electrons flowing through the wire just like water is flowing through a pipe. The diameter of the pipe, which we'll get to, is like the resistance. The amount of water that's actually flowing through the pipe, 2 gallons per second, 4 gallons per second, is the current flow. It's exactly the same concept. Just think of it that way. And then at the bottom there's the gravity analogy. It always flows from high to low. Resistance. Think of it like friction. It's exactly what it is. When the electrons flow through the wire, it's not a perfect conductor. There is always some form of friction, and therefore there's always some form of heat generated. Some devices in a system, their pure purpose is to stop the electrons flowing and to generate heat. It's not very efficient, but that's their purpose. Like I was saying earlier, the resistance is really like the diameter of the pipe. The wider the diameter, the less the resistance. The narrower the diameter, the more the resistance. And I put there at the bottom, off topic, superconductors. Superconductors actually have zero friction, zero resistance. So that's something that's coming down, hopefully, potentially in the future, where there'll be all these computing devices that maybe run at 4 degrees Kelvin. Probably not. I think you can get superconductors a little bit higher temperature than that, but they will generate no friction, no resistance, and no heat. And therefore, they will be capable of extremely fast computing. But I think that's decades, maybe not in my lifetime. Okay, so now we can come back to Ohm's law and better understand, with those basic concepts of what is voltage, what is current, and what is resistance, we can better understand what it is when we say V equals IR. And again, it's easiest to use the analogy, and I've got this water analogy here with the ratios. If I have a closed system with water, and there's a certain amount of pressure and a certain diameter of pipe, if I double the current, if I double the water flow, if I want to double the water flow, then I need to double the voltage, or I need to double the pressure. Or I have to halve the resistance by increasing the width of the pipe. It's the way to think of it. It's all ratio based on that equation, V equals IR. If I double the resistance, in other words, if I narrow the pipe by a half, I'm going to half the current flow, because half as much water is going to be able to fit through that half narrow pipe. That's the way I think of it, and it works. The reason that V equals IR is useful for you if you want to play around with like LEDs. If you buy an LED off the store and it says its forward voltage is 2.7 volts, and you've got a 6 volt or a 12 volt circuit that's coming in, you can use Ohm's law to compute the actual value of the resistor that you need to make that LED light up appropriately, so that you don't burn it out and overdrive it with too much current. That's the use of Ohm's law. I've used it many times, like, what resistor do I need here? Sit down, compute it, calculate it. And again, coming back to this one, P equals VI or I squared R, they're both the same. This is really important when you're dealing with wattage and how much power your components are rated for. So a little later, I'll show you on these boards, and you may have not seen them, you may or may not have seen them before if you've actually looked on boards. Sometimes you'll see little tiny resistors, and sometimes you'll see these big honking white things, cement resistors. And if you go to even higher voltage applications, you'll see even bigger things. And the size of the resistor is how much current or heat it's able to dissipate. And that comes from this equation here, P equals VI. How much current is flowing through it, and what's the potential difference across it. And if you don't compute that correctly, the resistor will fry or blow. And an example, or alternatively, if you short it incorrectly with a higher voltage than it's rated for, you push V too high, the circuit is only rated for 5 volts, and you accidentally short 100 volts to it. You now put 20 times the amount of voltage across it that it was rated for, and you'll often end up with a very black resistor and a very black board. And it's the same thing. For argument's sake, you can say, I've got I'm like that character in Portals who can fall from crazy amounts of heights because she got spring legs on her. I think her name is Chell. She's rated to fall for 20 meters. Okay, that's her limit. But if you put her up at 100 meters and you throw her off, and she's not rated for that, it's exactly the same thing. You put too much current across your circuit, you'll blow it up. You fall from a height that's too high for what you're rated for, you'll break a leg. It's exactly the same thing. Again, the gravity analogy. Okay, so current is flow. Unfortunately, flow can happen in 2 directions. Even though I said that it always flows from the highest to the lowest potential, there is a case where current does actually flow back and forth. So it's a little hard to understand why it would do that. I don't want to get into the mechanics of why it does it and how AC is generated, unless you want to know how hydroelectricity works and all that kind of stuff. But the easiest way to think of AC is someone is magically switching the poles back and forth, and therefore causing the high-low points to reverse. And the frequency in which they reverse is the frequency of the alternating current. So I'll give you the concrete example of what comes out of your wall socket. What comes out of your wall socket is 110 volts AC at 60 hertz. What that means is that there's 110 volts of potential energy, and the poles are switching 60 times a second. And that means the current is moving back and forth 60 times a second. The multimeter here, and we'll get to that in a second in terms of what's the setting, where do I set it, how do I do that, will measure. It will measure AC or DC, but it won't measure both. It's not that smart. You're going to have to say, I want you to measure AC or I want you to measure DC. If someone tells you to measure DC, you need to put the multimeter on DC because you won't get the right setting otherwise. But that's a fundamental thing that you need to understand, that current can flow, it can reverse multiple times, and that's AC. And then right at the bottom there, electromagnetic induction and voltage transformation. I'll cover that a little bit because it's kind of interesting to know what that big honking piece of metal that's really, really heavy at the bottom of your cabinet does. And its job is to transform the voltage that comes out of the line, that's 110, into all the other different voltages that your machine runs on. Digital machines all run on 5 volts. And pinball machines run on different levels of voltages. And what they've done with this So what the pinball machine manufacturers have done is they've combined all of the required voltage levels for the mechanical aspects that they need in the game to come out of the transformer. And they've done a bunch of windings in there. And the windings are wire, and wire is heavy. But the bottom line that you need to take away from this is that the transformers work on AC. You really can't transform DC. You can regulate DC, but you really don't use a transformer for DC. You use it for AC. Another interesting tidbit is most everything that you're using today runs on DC, but what comes out of your wall is AC. So every device that you have that has some form of electronics in it has a transformer to transform it down to the appropriate voltage level for your DC operation, and we'll cover it later, perhaps a rectifier to rectify the AC to DC. Okay, circuit basics. Circuits are basically wires connected from point to point between different components. Each component serves a specific purpose, and often the components are rated for specific power or voltage. And again, as I said, you do not want to exceed those ratings, otherwise you will release the magic smoke. A schematic is a logical a diagram of the logical connections between the different components. This tells you how it's supposed to work in theory and in practice. But it doesn't show you how it's laid out on the board. And that's the biggest thing. If you want to understand what the designer of the circuit was trying to do, you need to look at the schematic. You can look at the board and you can follow the wires and you can try and reverse engineer the schematic from the board, but you really want to look at the schematic. And the schematic will often tell you what the components are and what the voltage is and how it's rated. I wanted to touch on this because it's kind of related when you open up the back box. If you have a modern machine, you know, at least a 90s machine, if you open up a Stern, now all you see is a PC in the back box, so it's a totally different thing. But if you open up an 80s or 90s machine, you'll often see a lot of boards in there, and it can scare you. And you'll have a manual, and you look at the schematics and go, what the heck is this diagram? What's it for? It's all about the logical connections between the 2 points. If you understand that, then you can go look at the layout. And layout is physical. And I'll show you an example of that later on with these boards and in the software that's used to generate the boards and how the schematics relate to the physical layout. But the way to think of it is schematic is logical, layout is physical. The physical layout also is, it's also the connection points between the physical layout must match the schematic. Otherwise, it's not logically correct. So you can put a whole bunch of components on the board, but if you don't connect them according to the schematic, they still won't work correctly. So there's a hand-in-hand element to it. Okay, so circuit boards. Now that we understand what all that voltage and current and stuff is, we can move on to what components are typically on boards. What do they do? And I tried to categorize them here into things where you can look at and say, oh, that's what this component does. That's what the part of the circuit that it's for. And the single most important one, as far as I'm concerned, is protection. Because if you don't put for argument's sake, if you overfuse, your fuse is there to protect a component. If you put a fuse value that's too high, you aren't protecting the component. So the way I like to think of this is a bridge. I have a bunch of cars driving across the bridge, and that's my current flow. Well, I have a checkpoint across the bridge, a device that's only able to handle 5 cars per minute. So what I do is I build a 1-lane bridge that only allows 5 cars to cross that bridge per minute. And therefore, I don't ever exceed the capacity of my checkpoint that's able to handle 5 cars per minute. Now, if I build a 2-lane bridge, I've doubled the capacity, and now I may potentially exceed the 5 cars per minute that device is able to handle, and therefore cause it to kick up a stink, or in the case of electricity, probably blow up. And this is why you should never overfuse, because the fuse is there, like your bridge, it limits. If you put too many cars on a 1-lane bridge, it'll probably collapse. Okay, that's fine. At least no more cars are getting across the bridge. And that's the purpose of the fuse. The fuse will blow, and it will stop more electricity from causing damage. The one thing that's also interesting with electricity is as soon as you turn that power on and you've got something wrong, it will destroy the component before you can turn it off. It's way faster than your hand. So that's the reason why the fuses are there. They'll blow instantly and they'll protect your component. So don't overfuse. And anytime you get a new game, go through it and make sure your fuses are correct. Because often, people who operate machines will put whatever fuse size they have on hand in your machine to keep it running. And you'll see that in a lot of the older machines that haven't been touched or restored. Aside from fuses, you can use circuit breakers. Circuit breakers are a modern thing. I think a lot of them are actually thermally driven. So when they heat up, They cause something to break, and that is what interrupts the circuit. You can put circuit breakers in your machine if you want to and have them resettable, but often a lot of the boards are manufactured so that they only take cartridge fuses. And unfortunately, fuses are like 50 cents a piece at their cheapest, so if you've got a problem on your board, you will probably go through a fair few fuses, in which case you may consider using a circuit breaker if you want to not have to go out and buy a lot of fuses. The other two major categories that components fall to on boards are passive and active. Passive components just sit there and do their job. They don't actually consume power. Often things like resistors and capacitors. Resistors just dissipate heat. Capacitors just store the energy, but they don't actually use it or generate it. And then there are active devices, the more complicated ones like diodes, transistors, or chips. And these are the basics that you'll see on a lot of printed circuit boards, and often these things you'll also see embedded inside chips. So you can put these things inside chips to make a chip, then you can take the chip and put that inside another chip to make another chip, and so on and so on and so on. Until eventually, when you deal with all this stuff and you look at modern technologies, everything is just embedded in one single chip that's sitting in your back, in the back box. If you open up one of those remakes, like the Attack from Mars or the Medieval Madness, you open up that back box, there's a tiny board in the back of it. And that's it. That's your CPU, that's your brains. You open up an older machine, the whole range of the board, the back box area is taken up. Though that's how it was in the 80s and 90s. Technology has come that far. And then finally, particularly with pinball machines, there's a lot of connectors. And the connectors run the wires and the circuit and the components and the current all the way to the other components out there in the playfield that need it. Okay, so, as I was alluding to earlier, this is Electron Vision. Sometimes people, I facetiously say to people, wait a second, let me get my Electron Vision. And it's because it really is, you can't see electricity. This thing can detect it, and when it detects it, it will show it to you on its display. It's a form of seeing it. So what does it measure? It measures some of the basic things that you'll need to troubleshoot. Continuity. Is there an electrical connection between 2 points? Resistance. How much resistance there is between 2 points. Voltage. Again, AC or DC. What is the potential difference between 2 points? Diodes. Diodes are kind of a special semiconductor thing. Don't want to get in too much to them, but basically you measure a voltage drop across them to see whether they're functioning correctly. Capacitance. Those capacitors store energy and then they release it when the conditions are right. Some of the more basic multimeters don't measure capacitance. This one does, but it measures capacitance in a capacitor that's out of circuit. And I actually have no mention of anything in circuit, so perhaps I should stop now and cover that a little bit. In circuit means the components are all put on the board and there are electrical connections between the points. The electrical connections in it can potentially interfere with your measurements by generating continuity between points that in isolation would not normally be there. So when you measure something on your multimeter, ideally you want to measure it in isolation, out of circuit. You want to take the component off the board. And this is really important with things like fuses. You can put your leads on the fuse ends in the cartridge and it can read continuous, but there might be a wiring on the circuit board that provides continuity between those two ends incorrectly. You could conclude that the fuse is good, even though it may be bad. So when you want to check components, ideally you always take them out of circuit. Now, that doesn't always work when the component's soldered onto the board and it's not in a socket. So then you have to kind of like, well, you can look at the schematic and figure it out, or you can just take the component off the board. Some people say, I'll just cut one resistor leg, lift it up, and measure the resistance. That isolates it. But the most important thing is, if you do measure it in circuit, be aware that you are measuring it in circuit. If you measure it out of circuit, it's always going to be reliably correct. And then this one also measures current. I've actually never used it to measure current, so I don't know anything about that. Okay, so how do I measure them? Different types of multimeters have different dials and dial settings on them. This one's kind of a crazy expensive one. It's auto sensing. It's got a whole bunch of things on it. But your basic one will have different ranges for what it is that it's trying to measure. I will try my best to describe, but different multimeters, again, like I said, have different ranges. But the symbols are often always the same. Continuity. A lot of multimeters will have an audio cue or a buzz. Actually, I think that might be the next slide. Nope. Okay. In fact, no, it's there. Continuity between 2 points, audio buzz. What you do is you put your leads on one end, you put your leads on another end after setting the multimeter to what looks like the sound wave sign, and it should produce an audio buzz. You should be able to hear it. It's really handy because you don't have to look back at the multimeter and see it read 0 ohms. So if you do get one, I'd advise you get one with that in it. So it's really, you can just buzz your points out and hear them. Resistance. Again, resistance is, continuity is a special form of resistance. It's 0 ohms. There's direct continuity between them. The resistance, you have to set your multimeter to what is I think it's the sigma, the Greek letter sigma. You have to set it to that. No, it's not sigma, it's omega, sorry. It's the Greek letter omega. You have to set it onto that, and some multimeters are not self-sensing in their range. And often if you don't have it in the correct dial range, it'll read some dot or some crazy value that it doesn't understand. So sometimes you have to have an idea of what range you want. Some of the smarter multimeters like this one, you just put it across the two leads and it figures out what the value is. It's often a little slower because it has to sense the range, but it'll get it right eventually. Again, with resistance, it's important because to measure as much as possible out of circuit, because there may be errant paths in there that provide the path of least resistance. It's much like anything in nature. Electricity or water will always flow through the path of least resistance. So even if you measure your resistor, if there is another path in there where the electrons can flow from point to point faster or easier, less friction, less resistance, they will do it. And because your multimeter actually doesn't watch the electrons flow, it only senses their flow from point to point, it will measure the path of least resistance. So again, you want to try, if possible, to take it out of circuit. Now, there are times when you can cheat, and I wouldn't call it cheating, I would call it being a genius, using your brain. Look at the schematic, and the schematic will often tell you the points of connections from where you're measuring. And if there's no actual connection on the schematic, then it's a pretty good, safe assumption that you don't need to take the component out of circuit. And I said, it's not 100% certain because, for argument's sake, you could have blown a component, released the magic smoke, and there could be carbon, soot, and dust all over that board. And carbon, graphite, conducts. And if that carbon is sitting on the board and it's conducting, it's providing an errant path of least resistance that your multimeter will pick up, and it's therefore not accurate. Again, there are a whole bunch of things can go wrong. If you understand the theory of how it works, you'll be able to look at it, hopefully, and say, well, this is a potential problem I want to try and avoid. Voltage. As I stressed, it's between 2 points, and it's either AC or DC. A very common thing I've seen on forums is people say, can you measure the DC voltage at this particular point? Often after the voltage 5-volt regulator on a WPC. And they'll turn it on, and they'll say, well, I measured 0. And yet the machine is booting and the LED's on. It's like, well, the LED's on indicating that there's 5 volts. How can you measure 0 volts? The answer is you put your multimeter on voltage AC, not voltage DC. It's really important to know what the difference is, why you're measuring it, and how to measure it. DC is different from AC. Make sure you measure using the correct symbol. So, coming to that. There are two symbols on your multimeter. There's a V with a straight line over it, and then there's a V with a squiggly line over it. And the V with the squiggly line is AC. Essentially, it's meant to represent a sine wave, which is how AC works. Like everything in nature, a wave is always a sine wave. That's how it works. So the voltage AC has the little squiggly bar over it, and it's always measured between 2 points, and there is no ground reference in AC. It's the reference between 2 points. In DC, often there is a ground reference, but again, it's only arbitrarily because we call ground ground. It can be between whatever two arbitrary points you want to measure the DC voltage between. And this multimeter has a special diode reading on it, and basically all it does is it measures the voltage drop across the diode to make sure that it's operating correctly. Often when a diode fails, it'll either fail completely open, in which case it will not conduct, or it will fail shorted, in which case it will read zero, it conducts straight across 0 ohms. In any of those two cases, it's bad. Okay, so now we can apply a little bit of these basics that we've got, and we can look at the pinball machine in whole and try and track the path of power, and why they do what they do, and how they do what they do. So what is the power distribution? Well, you plug it into your main, and in the wall comes 110 volts AC. And it goes through the main, it comes into this line filter box, the main box, where there's a service outlet, which is always on. Even though you've got a nice on-off switch underneath your machine, if you have a service outlet in there and it's wired from the factory, in other words, somebody hasn't messed with the wiring, it's always on. Then the line voltage, which in electrical terms is the hot and the neutral, comes out from the line box, and it goes into another big Molex connector, typically on a Williams machine, which either has 9 or 12 pins, which allows you to select which is a jumper setting that allows you to select the input voltage. And without getting into too much, the voltage select allows you to select the number of windings or turnings in the transformer that is being used to transform the voltage. Then it goes through the primary windings, the input set of windings, which it should either be typically 110 or 230, I think is the settings that they have, 115 or 230. And then there's a second set of windings in there. Actually, there's multiple sets of secondary windings in your transformer for the desired output voltage. And then there's a bunch of those wires that run all the way up to the back box head, where they're then distributed into different power. On later machines, for the higher voltage AC output, which is more dangerous, they put an interlock switch in there. So when you open the coin door, the interlock switch is interrupted. You don't get 20 volts, you don't get 50 volts, you don't get shocked accidentally. It can also work against you in the sense, if you're not aware of it, if you run the coil test and you expect the coils or the flashes to fire and they don't, it's because you didn't close the coin door. So you need to be aware of that. And then once it comes up into the back box, it comes into the power, on older Williams System 11 machines, the power supply board, or on more newer machines, the power driver board. But either way, those two boards take the input voltage, munge them, morph them, do whatever they need to do with them to make the rest of your machine do what it needs to do. Okay, so on a Williams machine, at least on the later machines, what are the lines that are actually used, and why does it need so many, and what are they used for? Well, the most important one, because it's the brains behind everything that you do on your machine, is the 5-volt regulated digital logic line. It's also the bane of most WPC machines, as Rob Carr was talking about yesterday with resets. The next most important one is the 12-volt regulated digital logic switches. If the 12-volt lines go off and you have optos, your optos will start behaving really badly and really incorrectly, and you'll wonder, why is this switch firing in a crazy way? And if it all roots back to the optos, you need to check your 12-volt regulated. The CPU uses the 12-volt regulated for comparison of switches. If the switch is closed, current flows, and the voltage is 0 when current flows. If the switch is open, current doesn't flow. There is a potential difference across the two wires. The voltage is 12 volts. The CPU senses that and says the switch is open. That's all the logic is. It's digital logic. It's either 0 or it's 1. It's either open or it's closed. It's either 0 volts or it's 12 volts. The other line that's 12 volts, and it's often confused because it does say 12 volts on both of them. One's regulated, one's unregulated. The 12 volt unregulated is used to drive more, I guess you can call it more analog things like motors. So if your game has a motor, Path of Adventure, Dracula, all sorts of crazy different things, then those will be run off the 12 volt unregulated. The difference between a regulated line and an unregulated line is that the voltage is kept at that level in order to do a comparison. And I don't want to get into too much detail, but basically a lot of the digital logic, it measures voltage level. If the voltage is 0, it's a 0. If the voltage is 5, it's a 1. Well, so then you can ask yourself the question, what if the voltage is 2.5? Is it a 0? Is it a 1? And this is digital, it's either 0 or 1. So what is 2.5? So the whole point behind the regulator is to make sure that the voltage is always 5 and it never drops to 2.5, so that you get a clear answer that's either 0 or 1. You don't want this ambiguity. Because you get confused, well, guess what? So the CPU is going to get confused as well. And then the bottom three lines are essentially power to make your machine look pretty. 18 volt lamp matrix, 20 volt flashes, and 50 volt solenoids, which provide the mechanical part. The solenoids, just as a kind of a side topic, the solenoid is an electromagnet. It takes electrical energy, it converts it to mechanical energy. That's all it does. The exact reverse happens at your hydroelectric plant, where it takes mechanical energy, water spinning a turbine, and converting it to electrical energy. Okay, and I think I've reached the end, and a lot of you have probably already seen it, but I have some boards up here to give you an idea of what different components are and how big they are. And I guess we've got a little bit of time left, so you can come up here afterwards if you're really interested, or if you want, you can come find me at the center desk, and I'll be happy to explain and show and tell you what it is that I do and don't understand. The one thing that I do want to stress is that you cannot see electrons. Don't fool yourself. If you look at a component on the board and you say, it looks good, I'm going to say to you, do you have electron vision? And the answer is going to be no, because you don't. But with one of these, you at least can start somewhere. That's the take-home point. Don't visually inspect components. Verify them with a multimeter. The number of times I've seen people say, that fuse looks good. Did you measure it? It's really, really important. Thanks for listening. Any questions?
Yeah, if anybody has questions, there is a microphone set up there on the edge of the seating area there on the far left side. And you feel free to walk on up and ask questions if you have any.
Hi, thank you for a very informative presentation. I really enjoyed it. The question is, you mentioned that there are jumper switches that are used to select the input voltage. That I assume is used if a machine is transported to, say, Europe, when they have 220 volts and 50 hertz, as opposed to 100 over 60 here, right?
That's correct.
Okay.
The frequency itself, typically in European countries, power nations, it's 50 hertz.
Yes.
The frequency is actually irrelevant. It's the voltage. So the way a transformer works is when electricity or current flows through a wire, it induces a magnetic field. That magnetic field also, when the field changes, when electricity flows, it generates a magnetic field. When magnetic field changes with a what's it called, a static magnet or a fixed magnet, that induces a current. That's Faraday's principle of electromagnetic induction.
Correct.
The ratio of the voltage that's coming in or coming out depends on the number of turns in the wire. So if I have 110 volts of AC and I shoot that current through and I have 1 times of the winding, the output on the other side with a 1x winding will be 110 volts. But if I have twice the number of windings, the voltage, and I can't remember, it's one way or the other. So again, my background is in electricity. I understand the principles of the ratio. But let's say for argument's sake, if I have double the number of windings, I'm going to get double the voltage. I think it's the other way around. I think if you have half the number of windings, you get double the voltage. The key here is that the jumper selectors that you select will dictate how many windings or turnings are on the input, because the output is always the same. The machine expects a 50 volt AC output, but it's transforming that from a 110 volt input, or in the case of Europe, a 230 volt input, 150, 100, 230. You want to double the number of windings, and the jumpers select how many turns on the primary side of the transformer. Frequency is irrelevant. The frequency is irrelevant because DC has no frequency. The DC always goes in one direction, from high potential to low potential, and it never swaps direction.
Understood. So the moral of the story is, if somebody gets to transport a machine across the Atlantic, they need to make sure that they get the jumpers right for the setting in that area.
Yes.
Because otherwise they will burn the machine.
Yes. So okay. The example is, the machine operates at 230 volts in Europe, and you ship it in a container, and it comes back here, and it's still wired for 230. Well, here's the thing. For the US, it's fine, because your primary transformer input is 110. So at 230 volts, the 50 volt side, the jumpers are set correctly, so 230 volts produces 50 volts on the output. If you input 115 volts, like it is here in the US, you'll only get 25 volts on the output. The reverse is bad for Europe. If you wire something for 110 here and you bring it over there and you shoot 230, you're going to get 100 volts on the outside. And that's going to fry stuff really fast.
Okay, thank you.
Okay, if anyone has any further questions later on, find me in the center desk. Probably not without the orange shirt. Thanks for listening.